what are we going to do today? Well, last time we talked about the derivatives of inverse trigonometric functions. Well, actually, first we defined inverse trigonometric functions. We had arcsine, and arc cosine, and arc tangent. And then we kind of vaguely mentioned there'd be an arc secant, and an arc cosecant, and an arc cotangent. Okay, so today we're going to talk about those, but not very much. Okay, because the methodology is exactly the same as we did before. Okay. We'll talk about inverse trig functions. Continued. All right. And then we're going to talk about a more general topic, which is how do you find the derivative of, well, just any inverse function. Right? So we've done it twice already. We started with the exponential function, and we used it to find the derivative of the logarithmic function. Right? Of course, you could also think about doing it backwards. If you had one, you could do the other. Right? We took trig functions, and we found the inverse trig functions derivatives. So is there some general procedure for if you start with a function and you know its derivative, can you find the derivative of the inverse function in a reasonably easy way? Okay, so we'll talk about that. Okay, so let's start just by quickly recalling the facts. So we had this function, the arcsine function, okay, which is sometimes written arcsine. This is not meant to be to the -1 power, as in raising it to the -1 power, it's just notation. And we figured out that this was a function whose domain is exactly the range of the sine function, namely -1 to 1. And the range, well, this was a specific domain of the sine function that we chose, namely -pi/2 to pi/2. And we knew that if you took arcsine and you found the derivative of it, right, we used, well, what did we do? We set y equal to arcsine, and we applied sine to both sides. Then we took the derivative using the chain rule, also called implicit differentiation. Okay? And we were able to cook up a nice expression. We drew a right triangle, solved things around the right triangle, and boom, we ended up with a formula which was 1 over the square root of 1 minus x squared. Okay, so this was a lot of fun. You can watch the video online now. All 14 lectures are online at this point, by the way. Okay, then we computed the arc cosine, which is, again, you could write as arc cosine. And this was, again, a function from -1 to 1. Right? And the range, well, it became the domain of some domain that you could restrict the cosine function to. And the correct one is 0 to pi. And we found that the derivative was, well, the rule is if you know the derivative of one of the trig functions, and then you turn that function into a co, right? So sine becomes cosine, then what do you have to add? Just a negative. So it becomes -1 over the square root of 1 minus x squared. And then at the end, I believe we looked at arctan. And this takes as its domain the range of tangent. And the range of tangent, remember tangent, right? It goes, right? It goes all the way from -infinity, all the way up to infinity. So this, whoops, I guess we really shouldn't use square brackets. So this takes as its domain all real numbers, right? But the range, well, we just choose kind of that principal block of the tangent function in the middle, right? Which is the same as the sine. -pi/2 to pi/2. Except probably we can't include these endpoints. And why can't we include the endpoints? Well, the way you want to think about it is this is tangent. It looks like this. course, it never actually hits these endpoints, so you don't want to include them there. Okay, and when we took the derivative, right, we got 1 over 1 plus x squared. Okay, so let's write up the corresponding results for the other three. Cosecant, secant, and cotangent. Okay. I want to start with cotangent because it's somehow the easiest. So you'll notice there's a parallel in the range here of tangent with sine. And that's coming from the fact that tangent is sine over cosine. If you do cotangent, well, again, it's going to go from minus infinity to infinity. That is, the domain is all real numbers. But now the range is going to correspond to the range of arc cosine, because cotangent is cosine over sine. Okay? And so the range is going to correspond to 0, infinity. All right, 0. That's obviously an infinity. Okay, now, using our rule of co, what is the derivative of arc cotangent? It's the negative of the derivative of arctan, right? Okay, because you just added a c, you took a co, right? You had tangent or arctangent, you add a co to it, so it becomes negative 1 over 1 plus x squared. So yeah, every time you add a co, you just put a negative. Okay, it's going to be the same thing with the secant and the cosecant. All right, cosecant. All right, so this is where things get weird. All right. So the reason why we're going to choose a real funky domain and range here is because we want the derivative to look nice. Right? If we choose a domain and a range which is continuous, just one interval, then you would have to throw an absolute value into the derivative. Okay? And nobody here wants to do that if they don't have to, right? So we put down a real funky range and domain, and okay, it takes care of the problem. But if you actually sit down and try to work this out, you'll see why an absolute value has to show up. Okay, so let's see. I'll use my cheat sheet, because these domain and ranges are funky enough that I don't remember them usually. So, okay, so first, the domain of cosecant that you're using is 0 to pi over 2. You don't include 0, okay, but you're going to include pi over 2. Now, why don't you include 0? Well, cosecant is 1 over sine, and sine is not defined. I mean, sine is 0 at 0. All right, so you don't want to do 1 over 0. Okay, but pi over 2 is okay, because sine of pi over 2 is just 1. So it's okay to do that. Union, and now we skip everything between pi over 2 and 3 pi over 2. Oops, sorry. Everything between pi over 2 and pi. So we skip a pi over 2, and we go from pi to 3 pi over 2. This just can't be right. Why can't it be right what I wrote? Well, again, sine of pi is 0, so you don't want to do 1 over 0. So you better not include that. But you can include 3 pi over 2. Okay, fine. If I look at these as my domains for cosecant, what will the range be? Well, cosecant is 1 over sine. Let's just write 1 over sine. Okay. So let's look on this interval. Between 0 and pi over 2, what is sine doing? Let's draw a little circle. Okay, so here's 0, and here's pi over 2. Sine is starting at 0, and it goes up to 1. Right, so you're getting all the numbers between 0 and 1. So what happens to 1 over sine as x ranges between 0 and pi over 2? Well, you get numbers, okay, when x is pi over 2, you get 1. Right? And then as it gets smaller, as it goes to 0, right, this sine of x goes to 0. So it approaches 1 over 0. Right? What is 1 over 0 approaching? Right? As the denominator gets really small, what happens to the fraction? It gets really big, right? So here, when you look at the cosecant function, right, and you apply it in this range, it's going between 1 and infinity. Okay, and so that becomes, right, the domain of cosecant inverse. Okay, at least on this part. Now, okay, what about on this part? Well, between pi and 3 pi over 2, okay, sine is again 0 at pi, and it goes down to minus 1 over here. So it's always negative in this range. Okay, it's at this point it's going to give you negative 1, and then the denominator is getting really, really small, so it's going to blow up and go to negative infinity. Okay, so this is also going to give you negative infinity and negative 1. Okay, so, and of course usually you write this backwards. Okay, so this, but I put it this way because this corresponds to that, and this corresponds to that. All right, now what is going to be the derivative? Well, you play the same game that we played last week. You say y equals cosecant inverse. Then you take cosecant to both sides. Right? So then you get cosecant of y equals x. And then you take the derivative using the chain rule and blah, blah, blah. Okay, you set up that triangle. And the answer is a little more complicated than the sign. It's going to be x, 1 over x times the square root of x squared minus 1. Okay. And if you didn't choose the domain in this nice way, loose definition of nice, if you just, were, for instance, or this range, right? If you just kind of chose some continuous interval, right, then this x would take on an absolute value. Yeah?
Well, because I learned the definition was 1 over square root of x.
1 over square root of x?
I mean 1 over absolute value.
That's right. So if you choose, that's exactly what happens. If you choose this domain or range differently, right?
But like how could a definition or a derivative change?
Well, the reason why is when we choose things on these intervals, right, all of our signs are going to, like when I say signs, I mean plus or minuses, are all going to end up being pluses. Right? If you chose this just as one interval, then you get a thing where the signs are going to switch. Okay? And so then you have to use an absolute value here. Okay? Both definitions.
Something besides x.
Yes.
Okay.
Both definitions are correct.
Okay.
Okay? It's just once you choose a definition, then your derivative is changed accordingly. So you can do it the other way. The other way is not wrong. You'll just notice they use a different definition for arc cosecant. And when I say different definition, I mean a different domain and range. Okay, and the same thing as what Stephanie was saying is going to apply for secant. I bet you learned that with an absolute value as well. Right? And so again, it's just a choice of what your domain and range are going to be. So again, I want to write down the range first. So this is coming from 1 over cosine, and so it's going to look the same, only now the endpoints are going to swap. Because now, when you do 1 over cosine, right, you don't want to allow pi over 2 as your x value. Because at pi over 2, cosine is 0. Right? So you can't have that. But you can do cosine of 0, which is 1, right, and get 1 over 1. That's no problem. And then, again, we're going to do the same thing here, but we have to switch which endpoint we include. All right, and of course, there's something very symmetric about these situations of sine and cosine. Right? As you go between these ranges, now cosine is going between 1 and 0 instead of 0 and 1. Okay, but when you take the quotient here, it won't matter. You're still going to be going between 1 and infinity. And on this interval, right, it's going to be going between, right, 1 and 0. or negative 1 and 0 rather. Okay, and so, but again, the whole interval is just going to be minus infinity to minus 1. So again, writing it in this slightly awkward way backwards, that's what the domain will be. And if we use the law of Co, all right, what will be the derivative? It'd just be the negative of the derivative of cosecant. So negative 1 over x times the square root of x squared minus 1. Yes?
Say you have like the inverse secant of x. Wait, isn't that supposed to be cosecant? If it's negative? Oh, wait, because you have secant negative 1.
Oh, do I have them backwards? I do have them backwards.
Yeah.
Yes. Of course, the co's should always be negative.
Yeah.
Okay, so the secant is not negative and the co is negative.
Okay,
And that's part of our law of co.
so if you had like the inverse secant of x squared, you would have to do 1 over x squared square root of x squared squared. Because you have to put the derivative for both x's. You have to put what x is.
Okay, let's write up what you're saying so that we all
Yeah.
will benefit from it. All right, so the problem you want to consider is the derivative of what?
So like x squared or secant, the inverse secant of x squared.
Like this?
Yeah.
Okay, so excellent problem. Right? What rule will we have to use on this? The chain rule, right? Because we have a function of a function. So the outer function is arcsecant, and the derivative of arcsecant is 1 over x root x squared minus 1. Okay? But we have to evaluate it at x squared. So everywhere we see an x, we have to put an x squared. Okay? So this becomes 1 over x squared, square root of x squared squared minus 1, times the derivative of x squared, which is 2x.
So you have to do it for both x's.
You have to do it for every x that you see. Exactly. Okay, and of course you can simplify this slightly. We'll see. One of these x's is going to cancel, and the 2 can come on top. So 2 over x root x to the 4th minus 1. Very good question. All right, why don't we do another example? Let's try computing the derivative of the arc cotangent of, oh, let's say 3x root x plus 4. Okay, so this is pretty gnarly. All right, what rules are we going to have to use here?
Chain and product.
We have to use the chain rule and the product rule, right? The chain rule, because we have a function of a function, and then look inside, this function is a product of two functions. Right? So we'll have to use the chain rule and the product rule. And, well, eventually we'll probably also have to use the power rule and the chain rule again and the sum. I mean, we have to basically use all our rules here except for the quotient rule. Okay, so let's just do it one step at a time. Just kind of do it piece by piece. All right, so we saw the derivative of the arc cotangent is negative 1 over 1 plus x squared. But here my x is 3x root x plus 4. So let's see. So I get negative 1 over 1 plus 3x root x plus 4 squared times the derivative of the inside function. That's what the chain rule is telling me. I'll do the derivative of 3x root x plus 4. But I'm writing root x plus 4 here I don't like. I'll write to the 1/2. That seems like a reasonable thing to do, I think. Okay, well let's see what we got. We can simplify this a little bit. And everything is fine up until I get this thing squared, right? When I square this, let's see, just term by term. I get 9x squared times, well, square root of x plus 4 squared is just x plus 4. So 9x squared times x plus 4. Okay, no problem. I wouldn't expand this at all. Times the derivative of 3x times x plus 4 to the 1/2. Okay, and this should be, will happen now for everybody. Okay, so let's see. We'll make this our first function. That'll be our u. That'll be our v. All right, and remember the product rule. uv prime is u v prime plus v u prime. So let's see. 3x times the derivative of x plus 4 to the 1/2, which is, see, we have to use the chain rule and the power rule here. 1/2 x plus 4 to the minus 1/2 times the derivative of x plus 4. But what's the derivative of x plus 4? 1. Just 1. We don't worry about that. Okay. Plus, okay, now we need to do v times the derivative of u. So u is 3x. What's the derivative of u?
3.
Just 3. Okay. Derivative of anything times x is anything. Okay, so we get 3, and then this gets fixed. X plus 4 to the 1/2. So it's this piece times this term in parentheses. Okay, and I wouldn't try to fiddle with this so much. It doesn't look very nice. Questions? Okay. They're just more formulas. Okay. At the end of the day, you're going to be able to write down a bunch of formulas. Okay, these are all my rules, and then how do I find the derivatives of all the trig functions and the inverse trig functions, and the exponential functions and the logarithmic functions. Next time we'll get hyperbolic functions and inverse hyperbolic functions. Okay, but at the end of the day, it's just a bunch of formulas, right? And you just need to know how to use them. Now, if you really want to understand this stuff, of course, you take more math classes, and take analysis, and learn about what limits really are, and it'd be a lot of fun. But for your purposes, right, we're going to just kind of filter out a lot of this garbage. We're just going to write down a little table of derivatives for you.
Do we use like a formula sheet on the midterm?
No. Definitely not.
Oh, okay.
Because, you see, in the end, the list of formulas to memorize is going to be very finite. Probably less than 30. That's not that bad, because most of them you already know. For instance, what's the derivative of sine?
Cosine.
Cosine, okay, see, that's very easy. Right, and so what's the derivative of cosine? Sine, okay, so that's 2 to the 30 some odd, right? You're doing great already. Sine. You won't need, if you sit down, and you just write them down on flashcards if you like. It's not that hard. Okay, you just write down all the derivatives that you know, and there's not that many. I bet you'll find out you already know most of them. And it won't take long to memorize. And you shouldn't be afraid of memorizing. Right? Most of the great learners in history have spent a lot of time memorizing. It gets a bad reputation these days, but memorization is really important. Okay, let's do another example, since we have very little time. When do we have till today? Is it 11:15? Okay. Yeah, we'll do one example more. All right, let's do another derivative. Let's do arcsine of tangent of cosecant inverse. As you're preparing for the midterm, note that I really love doing these chain rule problems. All right, so what do? Well, we have arcsine of something. So we're going to have to use the chain rule. So the derivative of arcsine is 1 over the square root of 1 minus the inside squared. So tangent of cosecant inverse 1, 2, 1, 2. Okay. Actually, I can put the square there. Okay. Times the derivative of tangent of cosecant inverse of x. Okay, now, as an exercise, I'd like you to use this triangle trick that we learned last time to try to figure out what this is. Okay? But for now, we'll just leave it. Okay, so what's the derivative of the tangent of cosecant inverse? Well, again, we have a function of a function, so we have to use the chain rule. What's the derivative of tangent? Secant squared. Right, so we get secant squared of cosecant inverse of x times the derivative of cosecant inverse. And again, you can use the triangle trick to figure out what this is. Okay, so I'll combine these fractions, and I get secant squared cosecant inverse of x over the square root of 1 minus tangent squared of cosecant inverse of x. All right, times the derivative of cosecant inverse, and we can just read over here, this is negative 1 over x, root x squared minus 1. So we'll put the negative out front, and we'll put an x, root x squared minus 1. And these terms you should try to simplify using right triangles. Right? Using just the same trick as we used last week. That's a right triangle. Okay. And if you missed the lecture on Wednesday, go on the web and watch it. And then you'll see what this trick is. And I'd say it's important that you know how to use this right triangle trick because I'm thinking of putting a problem on the midterm about it. That's motivation there. But it's also just a really nice trick.
Wait, I don't remember. I was here about like, can you just, what was that thing again?
So that's why I said go watch this the video because I have one more thing I really want to get to today. All right, but it'll be very obvious when you go and watch the video what I mean by the right triangle trick. Right. It was very much pointed out.
Which day did we cover that?
That's from Wednesday of last week. It's the very last, it's lecture 14, called, If You're There, God, Give Me an Arcsin. Alright, so in the few minutes we have remaining, I want to look at this more general question of what to do with the derivative of an inverse function. So, let f of x be a differentiable function. If f is 1 to 1, right? So if you can't find 2 points which are different and go to the same point under the function, right? And we said that the function is 1 to 1. Okay, so if it's 1 to 1, we can always find an inverse. Okay, at least if we restrict the range. Okay? So if f is 1 to 1, then f is a bijection onto its range. Okay, so it may not be an onto function if you make the range too big, right? But remember what we did. If the range was too big, we just got rid of the bad points that weren't hit by the function. Okay? So if we just looked at the range of the function, right, that which it actually hit, the target set, then it becomes a bijection if we know it's 1 to 1. Okay, once you have a bijection, what do you get? What's the key? I have a function, it's a bijection. I can build a new function called the inverse. Exactly, right? What do? I have this function, it takes boom, 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 all these points going across, right? How do I build the inverse function? All right? Well, every time a point goes to here, it ends up somewhere. And it's the only point which gets sent to, right? This one, boom, goes to here. And there's no other point which gets to that same point. Okay? That's why it's a bijection. How do I go backwards? Well, I just take this arrow and turn it around, go the other way. Right? If I started here and ended here, that's one function. The inverse function goes back the other way. Okay? So I have an inverse function once I have a bijection. Right? Well, you can ask all sorts of questions about this inverse function. I knew my function was differentiable. What did differentiable imply? Remember we had this, you had to go to the club, right?
Continuity.
You had the continuity club, right? Of course, if you go into the VIP lounge, you have to be differentiable. Okay? But if you got into the VIP lounge, then you definitely were already in the club, so you're continuous. Okay, so first question, okay, is the inverse function, f inverse of x, continuous? All right? If I have a bijection in the club, is its inverse also in the club? Right? It's kind of like asking, you know, in this world, is there somebody for everybody? Right? Imagine that, you know, you're this wonderful person, and there is a person for you, but they're not on this planet. Right? They're in another galaxy. I mean, this would be really horrible, right? You're one person in the universe, just isn't on the same planet. Okay? Well, the same thing happens here, right? You're wondering, if I have a function, okay, which is in the club, we know it has an inverse function if it's a bijection, but is that inverse function in the club too? Are they going to meet up? Are they going to hook up? Is it going to be a lot of fun? Who knows, right? Okay, so that's the question. Is it in the club? All right, and of course, if it is in the club, you can ask, is it also in the VIP lounge? So if the above question has yes as an answer, then is f inverse of x differentiable? Two very reasonable questions to ask. Okay, so the answer to this first question is going to be yes. I'm not going to prove it. It would be fun to do. We don't have the time. It involves the intermediate value theorem, the extreme value theorem. There's lots of good stuff built into it. Okay, so if you have the time, you know, come by my office. I'll show you the proof. It's really nice.
Really?
Yeah, it's a lot of fun. Okay, but for now, we'll just take this as true. If you have a continuous function, right, which is a bijection, then its inverse is also, well, of course, its inverse is a bijection, but it's also a continuous function. Okay. And we're going to prove, though, using this continuity, that the answer to this question is also yes. So if you have an invertible function or a bijection in the VIP lounge, right, then its soulmate, its inverse, is also in the VIP lounge. And yes, we will have a love connection. So the answer to this is also going to be yes, and we're going to prove that. The proof, right, well, we have to go back to the limit definition, but it's not going to be so. It's actually going to be pretty short. With one minor modification to our definition of a limit, of a derivative. All right, so let me just set up a little notation. I have a function, f, right, and I write y equals f of x, which is kind of the standard way to write these things. So if I put in x, then I get out of y. And let's say if I choose, I'm going to choose some point. Right? So choose some point A in the domain of my function. change things. Let's not call it A. I'm really tired of using A. Let's use subscripts. Let's call it x sub 0. Okay. This will be a little more standard notation. I'm going to set y sub 0 equal to f of x 0. So if I take this specific point, x0, and put it into my function, I get some value out, and I call that y sub 0. Okay? Okay, now, if we translate this into inverse functions, so let's assume f is a one-to-one, okay, hence a bijection onto its range, differentiable function. Okay, so it has an inverse. And so I know that I can apply the inverse to both sides of this equation. And remember, what is f inverse of f of x?
X.
Just x. Okay, so f inverse of y is x, and if I go to this specific point, f inverse of y0, all right, should be x sub 0. Okay, so I have these equations that I can play with. Okay, now, let's write down the definition of the derivative. We're going to do it in a slightly different way. First, let me write it the way you're used to. So I want to do the derivative of the inverse function. Okay, so let me fix it at a point x0. And I'm going to add something, well, first I'll start like this. This is what our definition of the derivative looks like, normally. Okay? Now remember, the way we wrote down this quotient is that we were actually looking at rise over run. Right? This was supposed to be how much the function changed in the y direction, divided by how much the function changed in the x direction. Right? And actually, when we originally wrote this down, we wrote x plus h minus x. Right? Because it started at, actually, x0 and x0. Okay, so because it started at x0, and it moved to x0 plus h. Okay, so, and of course, the distance between these is just h. Right? And it went from f of x0 to f inverse of x0 plus h. Okay? Now, as h goes to 0, this point is getting closer to x sub 0. Yeah? No doubt about that. So, another way to write this is to say the limit as x approaches x0, and I'm just going to replace this by x. Okay? So I get f inverse of x minus f inverse of x0 over x minus x0. Okay, so there's no real change. As h goes to 0, right, this point is getting closer to x0. As x goes to x0, this point is getting closer to x0. I haven't changed anything. I've just changed the names to protect. Well, I don't know how innocent or guilty these things could be, but they are. Okay. Now I play a seemingly idiotic trick. Okay? I'm going to divide the top and bottom of this function by the numerator, which is going to give me a 1 over, well, this is x minus x0 still, divided by this, well, formerly numerator, now denominator. Okay? Do you agree? This looks pretty idiotic to do.
Yeah.
Very good. I appreciate your support. Okay. Now, this x, we know that this x is the same as f inverse of y, and the x0 is f inverse of y0. Okay. So I can use that in a very nice way. Right? And what about this f inverse of x? Well, we actually, okay, so you have to excuse me, all right? I changed my x's and my y's somehow. Okay, here, I always wanted my f inverses to see y's, all right? All right, and my f's to see x's. So we play a little game. We turn all these x's into y's, because that's what the f inverse should really see are the y's. Okay, so you have to do that really quickly. Okay, and then all the formulas will match up correctly. And that's how you figure this out in the first place, is you do it wrong, and then you figure out, oh, I really should put y's in. Okay, so, f inverse of y, I know what that is going to be, right? That's going to be x. Okay, and f inverse of y0, that's going to be x sub 0. Okay, so that's going to be the correct denominator of a derivative. Okay, how do I get the correct numerator? Well, y, I'm going to write in the following way. F of f inverse of y minus f of f inverse of y0. And then on the bottom I have, well, f inverse of y was x, and f inverse of y0 is x sub 0. Okay, now why do I do that? Well, what is f inverse of y? Well, we just said f inverse of y is x, and f inverse of y0 is x0. So,
It's time to go.
oh, we're almost at the end. Please indulge me. I can rewrite this as the limit y goes to y0 of 1 over, this is f of x minus f of x0 over x minus x0. Okay, now, f was a continuous function. Therefore, f inverse was a continuous function. That was, right, the thing I said it's true, but we won't prove it. That means that as y goes to y0, x goes to x0. Okay, so I can replace this limit with an x and an x0. And now, right, these two limits are both going to exist. And so I can put the limit on the inside.
No way.
Yes. Okay. And what is this limit down here? Well, this is just the derivative of f at x0. So this is 1 over the derivative of f of x0. Which means we now know how to find, right? This whole process, right, gave us, right? You look at f prime of x0, I mean f inverse of x0, and you take the derivative. And it's just 1 over the derivative of f at x0. Okay. So next time we'll embellish this a little bit and do it in an example. Okay. Apologize for going well over time.